Hi, my name is Maggie Byers, and this is part 1 of exam 1, which I'm going to be talking about the chemistry of water's physical states. In question 1, it aims to understand how water transitions from a liquid to a solid state, which is ice, or from a liquid to a gaseous state like water vapor. To be able to understand the chemistry of those two states, I will first go over some important features of water's liquid state. When I talk about water, it's important to know that I'm talking about the purest version of water, like distilled water. I'm going to begin by talking about the electronegativity and polarity of water. Electronegativity is the ability to attract electrons. Atoms of different electronegativities form a covalent bond, and their unequally shared electrons can create a pull. Electronegativity can be determined by using the bottom left chart of the periodic table. Electronegativity's trend increases from left to right across the periodic table and from the bottom to the top, making oxygen have a higher electronegativity than hydrogen. And this also creates a pull, which can be shown by the red arrows in the image on the right. And this results in a partial negative charge on the oxygen and a partial positive charge on the hydrogen. The partial negative is in green and the partial positive is in blue. Because of this uneven distribution of charges, water is deemed a polar molecule. Now I'm going to talk about the intermolecular forces of water. Since polarity of water is understood, we can now look at the intermolecular forces of water. Look at the image on the left. Because water is polar and has a slightly negative end, oxygen, and a slightly positive end, hydrogen, it can readily attach to other water molecules and form hydrogen bonds, which are represented by dashed lines. Think of magnets. The negatively charged oxygen on one water molecule wants to attach the positively charged hydrogen on another molecule. Now I'm going to talk about water in the liquid state. In this state, the water molecules have enough kinetic energy to break free from their fixed positions. Though they look locked into place, they can move around each other. So the water molecules are tightly compact but still slide and flow around. I don't have a video, but I can show through this. Though they look, the hydrogen bonds that hold them together are not permanent. Instead, they are being constantly broken and reformed as the molecules move. This continuous breaking and reforming of bonds happens because there is heat in the system, and it gives the molecules motion or kinetic energy, allowing them to keep moving while never separating completely from one another. Now I'm going to talk about chemistry of the gaseous state. And as I previously stated, we are talking about the purest form of water. So for distilled water, the known point for water to become a gas is at 100 degrees Celsius. When the heat of water is raised, the kinetic energy increases and causes the hydrogen bonds to break completely. This allows the water molecules to escape into the air as gas and is commonly seen as steam or water vapor. The molecules are far apart and they fly off into all directions, but they still collide and bounce off other water molecules. I can show this through clicking back and forth, like the liquid. So they're far apart, but farther apart than the liquid state, but they're not tightly compact at all. Now I want to talk about the chemistry of the solid state. For pure water, the freezing point is at 0 degrees Celsius. When temperature of water is reduced, it freezes, and the water molecules form a crystalline structure with a hexagonal arrangement. This hexagonal arrangement causes the molecules to be held further apart than they are in the liquid state. A good example of this is potholes in the roads. Water can seep into the cracks in the asphalt, and it freeze and expand. Over time, they melt, and this process will be repeated. The crack will become bigger, and eventually it will break the pavement. When the temperature of water is reduced, the kinetic energy lessens as well, causing less motion of the molecules and insufficient energy to break the hydrogen bonds. So as you can see, they're tightly packed, but they do not move around very much at all. The molecules are more tightly packed than in the liquid form, and this gives ice a higher density than the solid. Also, think of icebergs for this scenario. It seems impossible that something so huge can sit at the top of the ocean, but because of the chemistry in water, this natural occurrence is able to appear. Water is unique from other liquids because when other liquids become solid, the molecules are packed more tightly than the liquid, giving the solid a higher density and allowing the solid to sink in the liquid rather than float like ice does. And finally, I want to talk about the effects of impurities on the gaseous and solid states. For this example, I've drawn water with a low concentration of salt, and water with a high concentration of salt. I've stressed this whole presentation that water is distilled and without impurities. This is because pure water has a known freezing and boiling point, aka the point it becomes an ice or gas. If impurities are present in the water, it can alter the freezing or boiling point. To understand this, imagine salt is added to the water. This will decrease the freezing point of the water, and the higher concentration of salt, the colder the temperature that is required to freeze it. When salt is added, it interferes with the hydrogen bonding between the water molecules. This makes it harder for them to connect and form ice crystals. A good example of this is why in the winter salt is placed on the roads, and it helps prevent ice from forming. That's all for my presentation.